Hi, and welcome on our next session here on parallel Bayesian optimization. So why are we interested in parallelizing BO? Well, I guess to most of you this might be rather obvious. So first of all, most of the computation hardware that is usually available to us nowadays is inherently parallel. Yeah? So usually have multiple cores available to us, multiple nodes, multiple GPUs. And especially because we're using Bayesian optimization because we want to optimize an expensive problem. Yeah, so this expensiveness is, I don't know, one of the core challenges. So I guess we might be obviously motivated now to put this parallel hardware to good use. On the other hand, Bayesian optimization is I don't know, at least in its vanilla version at first glance, an inherently sequential procedure, right? So we're just producing one point after another in each iteration of BO, and then we have to wait for a long time until this is evaluated. Now, of course, we could take a very, I don't know, simplistic perspective and say, okay, who cares? We're producing one point after one point after one point, but this evaluation of that point, that's the costly thing. And maybe we can simply parallelize this evaluation C of lambda and use all of our parallel hardware to make that thing here faster, and then potentially everything is solved. In machine learning, there are good chances that this is maybe possible. So because usually we resample our models, yeah, so there might be, multiple cross-validation folds we want to compute, and these are embarrassingly parallel. Maybe we can, parallelize the training of our machine learning model. But very often, this is technically not super simple. Let me remove some of these things here on the slide. And maybe this is not convenient from a technical perspective. Maybe, we could easily parallelize the cross-validation, but we're only using 3 folds, but we have 50 cores available. Well, then, we might only be conveniently be able to use 3 of those, right? But we want to use all 50. So it might be, still quite attractive to talk about how to compute a batch of Q points simultaneously in each iteration of Bayesian optimization. And this is what I will discuss here for a couple of slides. And then I will even talk about how to create a simple asynchronous version of Bayesian optimization, which is also, as you will see, not that hard. So you should know that there's a certain trade-off. Of course, this is very nice to now create multiple points and evaluate them in parallel. And this will create a certain, wall clock speed up because of the assumed parallel evaluation of each batch. On the other hand, you now have fewer feedback rounds for your model. You have less chances to, learn something about the structure of your cost function and to optimally place points. So making this guy here too large, although you have many cores available, might also be detrimental. On the other hand, we have already discussed that, especially in HBO and AutoML scenarios, random search is sometimes hard to beat. Random search, not mainly, but only explores the search space. So if we would just get like the exploration aspect right in this batch parallelization, this might already be something that's, worthwhile or good or okay. Okay. So what is the core challenge behind batch parallelization in BO? So as I've already said, the acquisition function is, the types that I've discussed until now is the design for figuring out placing one candidate at a time, right? So if we would, for example, naively optimize this and then from the optimization trace propose the top Q maximizers of this acquisition function U here. This obviously, I'm not sure whether I even have to say this too much or I'm even going to visualize it now, but it should be kind of obvious that this will produce near duplicates, right? They cluster around the current global peak of U that we have found, and this pretty much wastes all of the evaluations except for one. And I've used the Brownian function here. We've seen this a couple of times. You can see here in yellow the, initial design or the points currently in the archive, and I'm now trying to propose 8 different points in a batch. And what you can see here in the background of the plot is the most interesting part of the plot. That's the expected improvement landscape. Yeah? So we are fitting our surrogate model on these yellow points here, and then we are establishing the EI landscape and optimizing that, and then I'm returning the top 8 candidates from this EI maximization, which is of course stupid, right? Because now all 8 points get pretty much placed here. What I would like to have is something where maybe a point is placed here, a point is placed here, a point is placed here, here. So yeah, where I can exploring all of these interesting bumps in the EI surface. A nice diverse batch where the points are reasonably placed. They are all placed at points of high EI value, but they're also reasonably far apart from each other, and that should happen in a nice balance. So the most, I'm not sure whether I want to say obvious thing, most natural thing, let's put it like that, would be to extend the acquisition function definition, especially the EI definition, to a batch version. So in order to denote batches now, I will use superscripts here as before, but I will put them in these brackets so we can distinguish them a little bit in notation from the design points from the archive. So I could now say, hey, I want to have a QEI batch acquisition function thingy thing, and that is simply the expectation of my improvement. But I'm also, so here in the inner part, we see this, let's say so we compute now the expected improvement across the whole batch, and we take the best improvement value from the batch. But remember, these things here are random variables, right? Or you can at least see them like that. So this thing here on the inside is still completely probabilistic. But of course, we now can take the expectation over this, how we are doing this for EI in general or for the normal EI version. So the only thing that I'm changing is I'm now taking here the maximum across the batch, and then I'm taking the expectation at the end from the outside. So this would reward the best outcome in the batch, and that naturally encourages diversity, right? So on the other hand, there is now no closed formula for this optimization problem, so you pretty much have to resort to Monte Carlo integration to compute that thing. So the next problem is that you have moved now from a d-dimensional problem, because d was the dimensionality of your configuration space, to a q times d higher dimensional optimization problem. You can do this in BoTorch. This is available to you. There is, for example, an extra reparameterization trick going on so that this becomes a bit more efficient. And then you can turn this thing here into this here is a nice function, right? The theoretical thing, right? But like I said, there is no analytic formula for this. So you have to do this Monte Carlo sampling thing. So this becomes stochastic. So you have to, invest some, intellectual effort to turn this again into a deterministic smooth function through this reparameterization trick. Then you are able to also get a gradients on that, and it's still going to be quite expensive. So maybe this is feasible up to something like, Q equals 20 or 30. There is this substantial overhead associated with this. So for that reason, it might be interesting to also talk a little bit about simpler alternatives, which are a little bit more heuristic, but still do sometimes work quite well in practice. So for example, there is the Krieging Believer. This is now also quite old. So like 15 years, by David Ginsburger. This is very, very simple. So you now produce your batch in a sequence. So you start with your first element of your batch, lambda 1, and you do this by normal optimization of the acquisition function. So usually it's going to be and you just do your normal thing, yeah, and you get your configuration from EI maximization as usual, as you would do in a non-batch version. What you now do to compute other more elements of your batch, where you are avoiding to generate new further elements of the batch which are very close to this guy here, you fantasize an outcome value for this thing. Of course, you're not evaluating that yet, right? So you don't know the outcome because you can only start to evaluate it when you have constructed the whole batch, but we are currently in the, I don't know, we're currently trying to do that, right? And we've only produced the first element of the batch. So we now fantasize a fake outcome value for this thing, refit our Gaussian process with this fake outcome value, and then produce the next by EI maximization. Again, we fantasize a fake output value, we produce the next thing by EI maximization, and so on. And putting in these fake values for these already created elements of the batch lowers the posterior uncertainty around these guys, which means EI collapses there, or any reasonable acquisition function will avoid creating a new point in the vicinity of these already evaluated points. So you are now exploring peaks elsewhere. So the only thing that is now left to, determine is how we fake in these fantasy values. And there are multiple options for this. So one is, for example, called Krieging Believer. And for that, you just use the posterior mean at this produced point. There's also constant liar. This uses a fixed value. So for example, you can take the minimum or the maximum from your archive of all of the observed cost values. And there's also, Monte Carlo fantasizing, where you, again, where you sample a value from the posterior. Yeah, and when you fantasize this, you, like I said, you refit your GP, you propose the next point by usual argmaxing of the acquisition function. You fantasize a value for that, and you iterate and you iterate and you iterate until you have assembled Q points, and then these get evaluated in a batch parallel fashion. And that this might work, I have visualized below here. So you can see again the EI landscape on the Brownian function with the same training points that we looked at before. And you can see now in iteration 1, we get this point here by regular EI maximization. Then, the red guys are what we have constructed in the batch already. So, and the green guy is what we're currently generating in this loop of Krieging Believer or fantasizing. Yeah, I'm actually doing here the Krieging Believer version. And then we get another value here, and then we get another value here, and I would call that, a nicely diverse exploration of the AI landscape. There's something that's even simpler that was also proposed together with SMAC. So this is sometimes called QLCB, so it might be a little bit confusing, the different versions of that. But here is a very simple way to exploit the structure of the lower confidence bound acquisition function to create a batch parallel version. So remember that in the LCB acquisition function, we have this annoying tau. Let's not call it a hyperparameter, let's call it a control parameter, right? And we don't know how to set that. And setting tau differently will give rise to different, acquisition function landscapes. So in QLCB, we treat this as, something good and not something bad. So we can actually now sample different tau values. So we sample as many tau values as we have cores available, we sample Q, because we want to create a batch of size Q. We usually sample them from an exponential distribution. And then we have Q different acquisition functions, LCB type acquisition functions, which all encode different mean uncertainty trade-offs, right? And if we now optimize them, the batch somehow spreads automatically. This will not magically work perfectly, and if we are unlucky or if our tau values are too close to each other, then we might not get a perfect diversity. On the other hand, this is embarrassingly parallel. This is extremely simple. Sometimes this does work quite well. If you want to have an extremely simple parallel BO version, you might want to use this here. There is also Thompson sampling, where you get parallelization nearly for free from that. So what you can do by Thompson sampling is you can draw a sample path from the posterior of the surrogate. Remember, it's at least if you would fix observation points, so to speak, you're drawing your sample path from your Gaussian process is pretty much just sampling from a high-dimensional multivariate Gaussian. So you sample these paths, and then now you simply propose the minimum of the cost. You don't even do any type of acquisition potentially on this. You just propose the minimum, because all of these are like stochastic versions of your Gaussian process. And each posterior sample now gives you a different proposal, and you draw Q samples to get Q points. So don't have to do anything extra in here. Usually just because of this posterior diversity, you get a diversity in your batch. And yeah, this usually works quite well if you want to create like extremely large batches. If you work in higher dimensional BO scenarios. In lower dimensional scenarios, it might not work perfectly. And as promised, we could even create an asynchronous version of a BO. I would say from everything that I have summarized so far, this is potentially the most interesting, because I really like using this in practice, because there's like one problem for all of these batch parallel procedures, and this is that very often in AutoML and related problems, we have actually quite heterogeneous runtimes. So if you have like lambda 1, well, maybe I should put the 1 here, lambda 2, and lambda 3, and these are all different configurations. Maybe these are even pipeline configurations, right? So quite different algorithms are actually running when I'm evaluating these things. Maybe these are even, I don't know, these are all the same algorithm but different hyperparameter settings. Even then, the assumption is quite realistic that all of these have quite different runtimes. If that's the case, well, then if I'm evaluating my complete batch in a synchronous manner, the slowest evaluation will slow down the whole batch, right? Because everybody else has to wait until the whole batch is completed and until we can update our surrogate model and produce a new batch for evaluation. Asynchronous decentralized Bayesian optimization avoids this, and this works in a quite simple manner where we have like Q cores available to us, Q nodes or whatever, where we can run workers. So on each node, on each core, an individual worker runs, I don't know, infinite loops, so to speak, and we're keeping them busy all of the time. And we are reacting actually not in a per batch manner, but we are reacting on a single completion of a single point on a single worker. Okay, this is very vague, so how does this work precisely? So first of all, we're going to assume, and this is, the decentralized part of this is that, well, actually, let's just talk how this looks like. So then I guess the names become clear anyhow. So we're going to assume that on each node, here we have an individual worker. So in this visualization here, we have 3 of these guys. But all of them are connected to some shared database across the net. And this database contains pretty much simply a shared archive of all of the historic evaluations. And all of the workers have access to this archive. And what the workers will now do in an infinite loop is they will read. So if they are idle, they will read the version of the archive in the central database. They will fit a surrogate model on this. They will do a single point proposal by acquisition function optimization. They will evaluate that point and then write back the result. And this works asynchronously. And as you can also see, the logic is somewhat decentralized, right? Because the logic is actually here and not on a central node. There is one thing that we need to take care of here specifically, so that works particularly well. And that is that there's like multiple stages going on such a worker, right? So we are downloading the archive. Okay, that's pretty fast, right? It doesn't take a lot of time. Then we fit our Gaussian process on the archive. We propose a point, and then we evaluate the point. But the evaluation of the point takes quite a long time. And potentially, while we're evaluating that point, a new worker comes along, queries the archive again, and also now wants to propose a point. And that point on this, so maybe this guy here is evaluated here, and now worker 2 is also trying to propose a new point, but this point shouldn't be very close to this guy, right? So the archive will not only contain all of the completely evaluated configurations where we know the lambda and the cost value, it will also contain all of the pending design points, which are currently under evaluation. So, because if we do this picking one point at a time at a worker, this kind of risks duplicating, I don't know, in-flight pending configurations, so to speak. So for that reason, as I said, the archive also contains the list of pending configurations. So you have something like here, I don't know, lambda cost, lambda cost, lambda cost. And then for some of these guys, they are pending, and the database will look like that. And your worker will download this complete thing here and then fit a surrogate model on this complete thing. Of course, now it cannot fit on these rows, right? Because these rows, we don't know the cost value, but we already know what to do about this. So we get, maybe I shouldn't even delete that. So we know what to do in order to ensure that this thing here, or that we don't produce newly proposed points in the vicinity of this guy here, right? So we again fantasize the value. And we do this when we pull the archive. Now the worker that pulls the archive locally fantasizes costs for each pending configuration that is currently under evaluation on another worker. For example, by using, I don't know, Krieger Believer, or some constant liar, or some randomized version of this, and usually randomizing here is good. So we also get some variance into the process. And then we fit a surrogate model on this on this imputed data, so on the real and on the fantasy data. We then can fit our surrogate model on this, do acquisition function optimization, propose a point, and evaluate that. And at that point, we would also, again, write a new pending evaluation into the archive. And this, again, these fantasies, they inflate the posterior certainty at a pending configuration, and then other workers who are argmaxing the acquisition function, they will move elsewhere. And the batch, I'm not sure whether I should call it a batch, but these different asynchronously evaluated configurations, they will stay diverse enough. So here you can see how this might look like, right? So maybe we are now at this time point here now, right? And on this first worker, we have maybe already evaluated this guy, and this guy is pending. On the second worker, we have evaluated this guy, and this here is pending, and this is pending on the third worker. And let's assume that maybe this guy here is now fully evaluated. So we have to propose, I don't know, let's give it a completed box, so to speak. And now we have to create a new lambda 6 here by acquisition function maximization on this worker number 3. So in this case, we would download the complete archive. The complete archive would contain 6 points. Well, actually 5. It would contain 5 points, and lambda 1, lambda 2, and, well, lambda 3, they are all evaluated, but lambda 4 and lambda 5, they are pending, right? So for these pending configurations, we now have to do the imputation, the computation of the fantasy values. So let me maybe remove a few lines here. So for this guy and this guy, so you want to create this here. And for these two guys, we would now impute, fantasize outcomes before we fit our GP and before we do the acquisition function optimization to generate this guy here. Okay, this concludes our session on parallel BO. So what did we learn? So parallel BO proposes, usually if it's batch parallel, a batch of Q points to exploit parallel compute using, I don't know, top Q of The acquisition function is usually a very bad idea. We get these near duplicates. We don't want that. We want diversification. And we have covered QEI, QLCB, Kriegen-Believer, and these fantasizing techniques. Also Thompson sampling, and all of these are batch parallel versions. We also covered ADBO, so asynchronous decentralized BO, as an asynchronous workflows with fantasies for pending evaluations. This avoids idle workers under heterogeneous runtimes, which is quite nice. In practice, usually what you do is you want to like somehow match your batch size to your available compute. So maybe your available compute is somehow, I don't know, pre-specified. That's just what you have. And then you somehow try to match your, I don't know, your batch size to this, or the numbers of asynchronous workers you're using. This can get a bit messier and more complicated if you're also, I don't know, parallelizing the underlying cost function and you want to do both. So then that can get technically a little bit more complicated. But yeah, this is how you would go about this in general. And usually it's a good idea to also do some kind of a diversity sanity check. So while the thing runs, also most of these approaches are quite new, right? So none of them may be totally perfect. So you probably, as a sanity check, you want to monitor pairwise distances in your archive and then see whether you are still producing near duplicates and, I don't know, change something about the approach if that happens. So that concludes the session here. Bye-bye.